Hi. Today we're going to finish up the chapter in the notes on positive semi-definite matrices with an application related to distance realization. Okay, and the question in distance realization, the motivating question, is a really simple one, which is if I give you a bunch of distances between points, can you find points that have those distances? Okay, so first question, let's start with a really small example. So are there points P, Q, and R in R2 such that the distance between P and Q and the distance between Q and R are 1 away, but the distance between P and R is 3. Okay, and the answer is sort of very relatively easily no. Because if you have 3 points, no matter how they're um, no matter how they're oriented, then if you go from P to Q and then from Q to R, it has to take a further distance than going directly from P to R. Right? So this first thing says that the distance from P to Q is 1, the distance from Q to R is 1, but this says the distance from P to R is 3, which can never happen. Okay, and this is called the triangle inequality. If you have a triangle, then going along two sides of the triangle has to sum up to more than going along the last side of the triangle, because the last side of the triangle goes directly there, whereas going along two sides of the triangle, you take a detour. Right, so the answer is no by the triangle inequality. Okay, it's a really important inequality. It's really simple. It really is just going along two sides of a triangle has to be longer than going along the other side. Okay, and the way to state the triangle inequality is just that the distance from P to R has to be less than or equal to the distance from P to Q plus the distance from Q to R. If you go through an intermediate Q, then it needs to be a longer distance. Okay, and it turns out that actually this restriction is the only restriction. So if you want to make, let's call the distance from P to Q X, the distance from P to R Y, and the distance from Q to R Z, then if, so X needs to be less than or equal to Y plus Z, right? Y needs to be less than or equal to X plus Z, and Z needs to be less than or equal to X plus Y. But if these three things are all true, then there exist points with these distances. Okay, and I think you can probably see this relatively easily. The point is that you can put your first point wherever you want, doesn't matter. And then you can put your second point at the distance x away. And now when you place your third point, you need to be y away from P, but z away from R. So you take like a circle of radius y, and you want to place your point somewhere on there. At Q, you want to take a circle of radius z, but remember that x is less than or equal to y plus z, right? So if you take a circle of radius z, what you know is that it'll have to overlap this circle, right? Because the triangle inequality tells you that you have some overlap here. And then you can just pick either point here. I mean, they should actually be placed symmetrically. It doesn't look like it in the picture. And then that will give you all the distances that you want, right? So it's not so hard to see that as long as you satisfy the triangle inequality, it's possible to place 3 points satisfying the distances that you want. Okay, but the more general question is, if you have a bunch of distances in n-dimensional space, is there a configuration of points that achieves these distances, that realizes these distances? Okay, so the generalization. Given a bunch of pairwise distances, does there exist a set of points in Rn achieving these distances or realizing these distances? Okay, and it's not that obvious what to do. Okay, of course, the triangle inequality definitely still needs to be satisfied, right? In any dimension, going from directly from P to R should be faster than going from P to Q and then from Q to R. That's true in n space, but it turns out that that's not the only constraint. It's possible for all your distances to satisfy the triangle inequality, but for the distances to not be realizable. And there's a very nice example, small example in the notes, where if you're hoping for points, let me try to label them in the same order. P, Q, R, and S. And I'm just going to draw in what I want the distances to be. So if I want all of these distances to be 2, and I want these distances to be 3, it turns out that it's not possible to achieve this sequence of this set of distances between 4 points. There's no way that you can do it in any dimensional space. But that's not that easy to see, I don't think. And the answer is due to a theorem of Schoenberg from 1935. Schoenberg. 1935. And here's the theorem. So given some distances, dij, they're distances, so they better be non-negative, for ij ranging between 0, 1, up through n. So we'll start our indexing at 0 for this theorem for some reason. And certainly I want each dii to be 0, and dij equal dji for all ij. Okay, so in other words, what these dij's are going to be are the distances from my point I to my point j. And certainly the distance from I to I should be 0. And the distance from I to j should be the same thing as the distance from j to I. Right, so I'm just setting up the distances that they obviously first need to satisfy these two obvious things. Okay, then there exist points P naught up through Pn, and these points are actually in Rn, which is why we started the numbering at 0, I guess, because otherwise you have to write n minus 1 here, with the distance from Pi to Pj equals dij, if and only if the matrix M, whose entries are going to be Mij, this is going to be an n by n matrix with entries. So what is Mij going to be? It's going to be the following thing: 1/2 times di0 squared plus d0j squared minus dij squared. So set up this matrix for every I and j, compute this number. You can find points like this if and only if this matrix is positive semi-definite. Okay, so this is kind of an amazing theorem, I think. The fact that it's related to this matrix being positive semi-definite is probably not something that you would have guessed to start, right? Okay, so I'm actually realizing that the statement of this theorem is actually slightly wrong in the notes. This n here should actually be a k. So you should go back and fix this. This should be rk. in other words, it's not only talking about n plus 1 points in Rn, it's talking about n plus 1 points in any Rk. So it's a much stronger theorem than the one that's stated in the notes. This gives the complete answer to whether or not you can ever find points in any dimension if I just tell you the distances I want between them. Okay. Now, at the moment, it should not be all that clear to you why this distance realization is related to the positive semi-definiteness of this matrix. It turns out that it's actually a pretty elementary reason. But let me point out that it should be obvious at this point that the matrix M is symmetric. M is symmetric since, what is Mij? Mij is 1/2 di0 squared plus d0j squared. Whoa, don't know where that 2 came from. Plus, or minus dij squared. And mji is 1/2 dj0 squared plus d0i squared minus dji squared. But by the conditions that we put on the matrix, this value is the same as this value. This value is the same as this value. And this value is the same as this value because we made sure that the dij's equal to dji's. Okay, so we can use this theorem to show that, so we cannot place these 4 points in Rk, any Rk, with the distances that we want. This square in the top left corner, no matter which Rk I pick, I won't be able to find 4 points living in that Rk that have these distances. What is the matrix? Okay, so sorry, I'm just thinking of the movie The Matrix, but what is the matrix? I think that's actually a line from it. Come to think of it, did that movie come out before you were all born? I think it probably came out before most of you were born. Okay, so what are the distances I want? Well, I want d01 to be d10 to be 2, right? I want d00 is, of course, 0. d02 I said I wanted to be 3. And d03 I wanted to be 2. Then I need to know d1 is 0, of course. d12 I wanted to be 2. That's the same thing as d21. d13, which is the same thing as d31, I want it to be 3. Then d22 is 0. d23 equals d32 equals 2. And then d33 is 0. Right, so that is the distances that I want to realize. And then I just set up the matrix Mij. How many points are there? Right, this matrix is supposed to be an n by n matrix when I have n plus 1 points, so it should be a 3 by 3 matrix. I don't know why I started a new slide here. So what's the 3 by 3 matrix? Let me just sort of say how to get this first entry, right? This one is M11. So I'm supposed to take 1/2 times D10 squared plus D01 squared minus D11 squared, right? So that's D01 squared is 4 minus D11 squared is 0. So it's 4 plus 4, but then I need to divide by 1/2. So I should get 4. Which I think there's a typo in the notes, if I'm not mistaken. D10 squared is 4 plus D01 squared is 4 minus D11 squared. Yeah, okay, so there's a typo in the notes. Let me work this all out, and then I'll write the matrix down for you. Okay, so I'm back. I did 2 things. One thing is I moved this stuff to the previous slide because I have enough room for it. The second thing I did was I computed this matrix, and the thing in the notes is only off by a factor of 1/2. So the thing in the notes is almost correct, just missing a half, which isn't going to change whether or not M is positive semi-definite, because multiplying by a positive scalar doesn't change the sign of your eigenvalues. Okay, and this determinant of this matrix M is actually negative, which means that M is not positive semi-definite. Which means by Schoenberg's theorem, it's not possible to find a set of points with this, a set of 4 points with this set of distances inside of R3. Okay, so now we're going to work to prove the theorem, but first a little bit of a lemma, which actually we might as well prove. It's not so hard to prove. Okay, so given 2 points x, y in Rn, 2 vectors in Rn, it says that the length of x minus y squared is equal to the length of x squared plus the length of y squared minus 2x transpose y, which you can just rearrange to get that x transpose y is equal to 1/2 x squared plus y squared minus x minus y squared. Okay, and if you choose to write this dot product as the length of x, the length of y, and the cosine of the angle between them, then this recovers the law of cosines from, I guess you learn it in high school, but very few people actually learn it. Okay. Now, this is actually not so hard to see. It follows from taking the dot product 2 different ways, right? So the left-hand side is clearly the same thing as, okay, let me do it like this. This length squared is equal to x minus y dotted with x minus y. Or you can write it like this. Let's just use dot products. It's fine. And now you can just use the distributivity of the dot product, or the distributivity of matrix multiplication over matrix addition. Together, this is x dot x plus y dot y minus 2x dot y. And that's exactly length of x squared plus the length of y squared minus 2x transpose y. Okay, so this is just by properties of dot products, and this is probably the easiest way to prove the law of cosines. And the reason it's related is because if you have a vector x and a vector y, then what is the vector x minus y? You take x and you subtract off y. This is the vector x minus y. But then you can just slide it here. It has the same length as this, which is the third side of the triangle. So this is the length of one side of the triangle, this is the length of the 2 other sides, and this thing is the cosine of the angle between these 2 sides, from which you recover the law of cosines. But it's just a fact about dot products. This is how I remember the law of cosines anyway. Okay, but we can use this in order to prove Schoenberg's theorem. So proof of Schoenberg's theorem. Okay, so it says that a bunch of distances are realizable by a set of points if and only if some matrix is positive semi-definite. So we need to prove both directions. So first, assume that the distances are realizable. We need to show that matrix M is positive semi-definite. And I'm just realizing, based on these notes, that I haven't used this symbol that I introduced for it in lecture yet, so let's use it. Okay, now, if the distances are realizable, what that means is that there exist points, right? This is what we're assuming. There exist points P0 through Pn such that the distance from Pi to Pj equals dij for all I and j. Okay, and then a thing to notice is that if we may as well assume that one of the points is the 0 vector, because if you have a configuration of points with the correct distances, you can slide it down and it would still have all the correct distances. Right? So without loss of generality, we assume that P0 is the 0 vector. If it's not, you can just slide the whole thing down. Okay, and then I think the proof in the notes actually goes a little bit off track. There's no reason to define xi's once I've assumed that p0 is 0. So this will depart a little bit from the proofs in the notes. But then what's the length of pi? Once I've assumed that p0 is 0, this is the length of pi minus p0 because p0 is 0. So this thing is di0, which is d0i. So each of the pi's has length di0 because I'm assuming that p0 is a 0 vector. And also, if I look at pi minus pj, this thing was supposed to be just the distance from I to j, which is the distance from j to I. And this is for all I and j between 1 and n. Right, so p0 is like a special point. It's 0. I just slide it to the origin. And then all I'm saying is, okay, well, these, now that I've slid to the origin, the vectors p1 through pn all have the very nice property that their lengths are di0, and the lengths between them are still the distances that are required. Okay, now, by the lemma, what is pi transpose pj? Pi transpose pj is 1/2 the length of pi squared plus the length of pj squared minus the length of pi minus pj squared. Okay, all I've just done is I've taken x to be pi and y to be pj in this formula. Okay, but what is this? This is 1/2 times di naught squared plus d0j squared minus dij squared. Right? And this thing is the thing that we called mij in the matrix. So I've showed you how to get mij from pi and pj. Okay? Well, now it's just a hop, skip, and a jump to the following fact, which is if you set up a matrix where you put the columns to be these p1 up through pn, and then you take its transpose, so these are now row vectors, what do you get in the result? You get exactly, at each entry, you'll get pi transpose pj. That's exactly how you compute the product of two matrices. You dot the rows with the columns. And this is exactly the matrix of mij's, which is the matrix M. So just call this matrix B, call this matrix B transpose, which it is. We've shown that M can be written as B transpose B. In other words, M is positive semi-definite by that other theorem that told us that positive semi-definite is equivalent to being able to be written as B transpose B. So M is positive semi-definite. Okay, so really the entire content of the theorem comes from this little lemma, which we proved in one line. Okay, 2 lines for me, but 1 line for you maybe. Okay, and the converse is actually pretty much the same thing, right? So first I assumed that I could find points, and I showed that the matrix was positive semi-definite. Now I'll just go backwards. Suppose that the matrix is positive semi-definite. Suppose M is positive semi-definite. Okay, then by our theorem, what this means is that there exists a k by n matrix B such that M equals B transpose B. We have a theorem that says that being positive semi-definite is equivalent to being able to be written as B transpose B. Okay, now what we're going to do is we're going to write B in terms of its columns, B1 through Bn. Right, so each of these BIs is in Rk. It's a k by n matrix. What we're going to do is we're going to set P0 to be the 0 vector and Pi to be Bi for all I equals 1 through n. And what we're going to see is that the lengths between the distances between these points satisfy exactly what we want. Okay, why is that? That's because notice that since M is equal to B transpose B, this means that Mij, the ijth entry, is exactly Bi transpose Bj, which is pi transpose pj. So in particular, we'll have that mii equals pi transpose pi, which is the length of pi squared. But remember, by the definition of mii was di0 squared plus d0i squared minus dii squared. And d0i, maybe I should write this down, this was by definition di0 squared plus d0i squared minus dii squared. But by the conditions that we put on the dij's, this is just, sorry, 1/2 this. This ends up being just di0 squared. So what does this say? It says that if we take these pi's to be the columns of the matrix B, then their lengths are all the correct lengths such that their distance to P0 is equal to di0. Okay, so in other words, if you choose the columns of B for your points 1 through n, and you choose the 0th point for the 0 as the 0 vector, then the lengths are all correct to P0. Okay, what about the lengths between the Pij's? So further, Mij is Pi transpose Pj, which is, by definition, this thing was 1/2 di0 squared plus d0j squared minus dij squared. That's by definition. But we now see that Pi transpose Pj, we can use that lemma, that this is supposed to be the length of Pi squared plus the length of Pj squared minus the length of Pi minus Pj squared. But we just saw that the length of Pi squared is di0 squared, right? We saw that here. So these two quantities are the same, and these two quantities are the same. So you multiply by 2, you cancel off the correct quantities. This shows that the distance from Pi to Pj squared is equal to dij squared, which means that if you take the square root, because we assume that the dij's were all positive, that if you take the columns of B as your vectors, they all have the correct distance to the 0 vector as P0, and they all have the correct distance from one another as well. So this shows that if you just take these columns of B to be your points, then they have the correct distances, assuming that M was positive semi-definite, right? The M was defined in the way that we wanted. If it's positive semi-definite, then you can pick these points. Okay, notice also that this result even tells you what dimension you can find the points in, right? Because, again, as I pointed out before, this Bi is an Rk where B was a k by n matrix, right? So in order to find the smallest dimension in which you can find such a configuration of points, you just need to make sure that the columns of B are linearly independent when you are writing M as B transpose B. So this theorem and this proof are actually very constructive. If you have a set of distances you want to realize, you write down this matrix with these di0 squares plus d0j squares minus dij squares. Then that's if it is positive semi-definite, then you'll be able to find the distance realization. And you can use the stuff that we did in the positive semi-definite lecture a couple of lectures ago, where you take like the square root of you diagonalize it and you take like the square root of the eigenvalues along the diagonal to break it up into a B transpose B. And that B tells you what points you need. It's really quite an amazing theorem. Okay, so the content for this lecture and from the notes comes from a very nice little article about several results in distance geometry. That's exactly what this result is, right? It's what is the geometry to achieve these distances? And I think the notes also mention a really cool application of this to chemistry, right? So if you have some compound that you're studying, and you can use, I guess it's NMR, nuclear magnetic resonance, um, to determine the distances between the atoms, which is apparently something you can do in chemistry. Well, then what does your molecule look like? Well, you want to know what collection of points in 3 space has these correct distances. And this result that we just showed, that we just proved, gives you a way to find where the points are, and that tells you about the geometry of your molecule. I think it's a really cool application of this distance geometry. I mean, this distance geometry stuff, I think it's very beautiful. It's such a natural question. And the answer has to do with the positive semi-definiteness of a certain matrix, which I think is also pretty incredible. Okay, so this ends our section on positive semi-definite matrices. We're now going to start talking about polynomials and vector spaces of polynomials. So that will be our next section where we'll learn a bunch of stuff, learn a bunch of linear algebra, and then we should see maybe an application in that section as well. All right, looking forward to it. See you then.